Hey, this is Andrew McLaren. Today we're going to be talking about VSPER, is often how it's pronounced VSEPR, and how you can use that model to find the geometric arrangement of atoms, to find the shape of a molecule, and also these bond angles. So you should be able to solve problems involving anything related to like VSPER at like the AP Chem level is kind of what I'm doing. We're not going to do like molecular orbitals and how they form. That's more of like the college level. You will get to some of that stuff in college, but for now we're going to be talking about like this theory, how in general it works, why we're doing it, and then we're going to do some simulation to help you understand it because it's good to see it modeled, right? And then some how I would study these because this is something that you kind of have to memorize, and so we're going to go over some memorization techniques that work well with this, as well as some typical problems. When I think of VSPER, I think of shapes, and I think about this data table of shapes. And we're going to go over this a whole lot, right? But the first pass, you've got like linear, and this molecule would be called linear. We've got like the central atom here. It's represented by E, and then these two X's. Those are two other atoms. And then they're also showing if you've got some pairs, electron pairs in here. So this is like the same general shape, trigonal planar, but this one has some electron pairs in it. So you oftentimes see a data table like this, maybe slightly different. This one didn't have the hybridization of the orbitals, which is worth including. They talk more about that in like college chem, but it's important to recognize that these bonds, they came from S and P orbitals, and those changed their shapes to allow these bonds to be as far away from each other as possible. So VSPER, this stands for valence shell electron pair repulsion. So it's just the electrons trying to repel each other and get away from each other as much as possible. And we get the angles that show them being as far away from each other as possible. If we're talking about the most common angles, you'll typically see 90, 180, 120, and then like 109, 107, 110. There's a ton of things that are close to each other. Those all go with the tetrahedron shape, but sometimes if you have like an electron pair, it ends up kind of like pushing down on the other stuff, making this angle a little bit bigger and these ones a little bit smaller. So they're not perfectly identical to each other, especially when you have different sized atoms and electron pairs in there that take up different amounts of space. So whenever you're seeing 109, 107, if you're working with carbon, this comes up a lot because it forms 4 bonds, right? And the way I like to imagine this is like, 90 degrees is pretty easy to visualize. Same with 180. It's pretty easy to visualize. 120, I remember that by thinking about 360 degrees in a circle. If we split that up into thirds, 120, 120, 120, so you can kind of see that it has to be 120 between all of them. And then to remember 109, I know it's got to be bigger than 90 and less than 120. That's just intuition with me. And then I think about like the trigonal planar, how it's got like the 120 degrees. And if you were to put something right in the center here, that basically it's going to push everything down and closer. So they can't be 120 degrees if suddenly there's something on top of them. They need to kind of squeeze in and get a little bit closer to the other orbitals or other bonds. So it has to be a little bit less than 120 if we've got 4 things, because 120 was when we had 3, right? In general, that's what you should see. If you've got more things that you're trying to separate, there should be less space between them, in other words. So you might be wondering, why are we getting these angles? It has to do with hybridization. When we're talking about like maybe argon or xenon or any of those things, like in the end, or they're going to have a complete electron shell. So these are stable due to filled sp orbitals. And if you have like, maybe this is like the 1s and 1p, right? Or 2s and 2p, You can imagine there's going to be 2 electrons that can get put in these each, and so that's 4 bonds, right? So that's why for most things they can form 4 bonds, especially if we're talking about the smaller atoms, because they don't have like d orbitals. I need to do a whole video on sp and d orbitals and electron configuration. That is something that I've got in the works, something that I'm planning on doing. Just a brief review. This is kind of what it looks like when you have like lead, which is Pb. It's going to have all these different electrons being represented in its different shells, and it's filled out using this little tool. I mean, that's one way of remembering how to fill it out. It's not because of the tool. So that's a little bit of what's going on with those. Electron configuration and hybridization comes from these sp orbitals. Like if I have something that's like 2s and 2p, and I've filled those all up, I can only form 4 bonds, right? So on and so forth. It's really important to just kind of have a couple of these atoms memorized because they come up so often in molecules. And like hydrogen is, because it's in that first row in the periodic table and it only has 2 electrons, it only has 1 orbital to bond, right? So it's pretty much going to have 1 orbital where it's bound to something, like an H2O, like if you have water or something like that. Yeah, the oxygen has 1, 2, 3, 4 orbitals or possible bonds, but the hydrogen only has 1, right? So hydrogen typically only has 1. Carbon typically has 4. So like carbon, you're going to see a lot of the time having like something like this where it's got 4 bonds. It could also have these as like double bonds, right? And in that case, it's using up its 4 orbitals there. And then oxygen is typically going to have like 2 bonds and then 2 unbonded. That's very, very common that you see that in molecules. And then nitrogen, this tends to have like nitrogen, this is really common for it to have like an electron pair and 3 bonds. Super, super common. Nitrogen, in that case, it's filled up, it's 4 orbitals. We've got 1 orbital, 2, 3, 4. So it's got its 4 orbitals filled up when that happens. And then there's some kind of weird things that happen, but you're oftentimes going to see like phosphorus and sulfur in these problems. Phosphorus, because it's in the periodic table and it's higher, it hasn't got as many orbitals to work with. So it typically forms 4 bonds. The other things, as you get lower in the periodic table, you're going to get like not just S and P's that are hybridizing, but you're going to get D and even F orbitals that are hybridizing. As that starts to happen, you're going to start seeing shapes like this, right? There's more possible bonds because there's more orbitals, but these things, these don't happen. These shapes don't happen for like the first row and second row of the periodic table because they don't have enough orbitals to do that. They've only got S and P orbitals. If you're in that second row, you only have P orbitals, so you can't really do much more than that, right? So that's kind of why we typically see 4 bonds or orbitals, is because they don't have enough to hybridize to get more. So it's good to just have a slight understanding about hybridization, orbitals, valence shells, because that comes into play when we're using VSPER, especially when you're doing these things that have more orbitals versus less. You kind of need to know that, right? You know the periodic table. Go figure. Okay, I'm really excited for the simulation. It's honestly an amazing one from PhET. This lets you play around with the geometries and kind of move it and look at it from like different angles. And you can also wiggle around the outside atoms and kind of drag them around to move the molecule, right? So you can build these different arrangements. And I love this for just quizzing myself and then trying to see what certain things look like when I arrange them in certain ways, right? And so you can kind of see with this guy, we've got that double bond taking up one spot, just like a single bond, which is kind of hard to explain without going into the hybridization stuff, which is again pretty complicated. But you can see that this is that tetrahedron shape that I was talking about. And now I'm going to just put on a couple more. And you can kind of see, especially if we make that the top, this is like that, the three on the base, and there's like that triangle on the base, and then you can kind of see this triangle on the side here, another triangle on the side there, and they're on the back. So it kind of cool, right? Helps you visualize it, and you can see that this, it kind of looks like 120 degrees, right? If you look at it from that perspective, but you can actually see it's a little bit like, yeah, that looks like 120 degrees, right? So if you get the other thing directly behind it, but if you look at it, you can kind of see like, oh, these things, it was kind of like trigonal planar, but then something came along and made the others get a little bit closer. So it had to be a little bit less than 120. A lot of people will get really confused with these larger shapes. So I wanted to talk about them a little bit. So we've got tetrahedron, and then you've got your trigonal bipyramidal. You can see that this is basically the trigonal planar, the three things 120 degrees away from each other, but there's something on the top and the bottom. So those push on the trigonal planar stuff like up and down equally. And so that's kind of why you see like the 120 degrees here, and then there's, it just so happens that there's these other two on the top and the bottom directly across from each other. It's kind of like you've combined a linear molecule going straight up and down and a trigonal planar in the other plane that it's going through. And yeah, that's kind of an interesting one. There's also like octahedral and like a number of other cool little things that you'll see. Like let me get rid of one of these. Yeah, let's do like that. Seesaw. This is a common one where I had a student that I was tutoring. I was like, what's going on with seesaw? I get so confused by that. The way I think about it is that it's kind of like, in the park when you see like seesaws, that kids would like, maybe one kid's sitting on here and another one's gonna sit on there, and then they're jumping up and down and seesawing back and forth with each other. That's the idea, is that like these are like two legs of the seesaw, and then these are like kind of like the two seats. And you don't really see the lone pair and the geometric shape. So we don't really think of that as part of the shape of the molecule. It does help determine the overall shape, but we don't include it in the name. Like that's why these things have different names. And then let's maybe do another one. Square pyramidal. Yeah, you can kind of see that actually. It looks like a square base. If you make this go to the bottom, there's a square on the base, right? Like four corners, a square. And then on the top, there's this top part right there that's a pyramid. So if you connected these, you'd get something that looked like a pyramid. So that's a really kind of a cool thing. Also, you can get the bond angles, play around with all of those as well. It's very, very flexible. In addition to that, what's really cool is that they've got all these molecules. And interesting to note, water is not exactly 109. It's a little bit different. Right? If you were to look at the model, it actually would give you something like this, but given the size of electron shells and everything else that's specific to this chemical, it's off from the expected angle just slightly. But that's okay, because it's not 120 or 90. It's off by just a little bit. So you can see what these things actually look like and kind of play around with that. Very, very cool. I would encourage you to try and build chemicals if you're like, I can't imagine what this looks like. If you have, is it aphasia, I think? When you can't actually physically, or not physically, the opposite, like imagine things. This stuff's going to be very difficult to do. And I would highly encourage you playing around with like physical model sets and the simulation to kind of see the angles and be familiar with them, right? And then, Yeah, let's do that one. Yeah, remember this is what I was saying. Like nitrogen typically will have 3 bonds in an electron pair. It's very satisfied with the electron configuration when you have that. Really, really cool. Again, look slightly different in the experimental model versus what we actually see in real life. And here we go, some examples of those larger things. Also, kind of cool. Check this out. I mean, that isn't actually what happens with the chemicals, but you can imagine it doesn't matter which one of these is the um, electron pair. The other ones are going to be arranged in that configuration so it's stable. All right, that's the sim. If you're trying to study VSPER, you're probably running into the issue where you're forgetting the name for a shape. And it's really, there's a lot of similar shapes. So what you need to do is kind of chunk them and put them together and study them using either a physical model or that simulation and quiz yourself on that. And I would also use like try and cover that up, right? So if you had like this table and you probably have like, if you're in a chemistry class, you probably have a teacher who has this printed out as a resource for you. Go ahead and cover them up. Like go ahead and cover up the name of this one and try and try and name it, right? Or vice versa, cover up the shape and try and draw it. And so that will help you get some familiarity, is just giving yourself these little checks. And you don't have to do this for all of them. Just pick the ones that you're forgetting or getting kind of mixed up. So if you've done this and you're like, yeah, I'm good on that. Yeah, I'm good on that. I'm pretty good with these guys, but I need to study these. And then maybe you're like, okay, like I get like linear and this one, but these ones I need to practice more. I keep on forgetting their names, right? So you can kind of mark what you need to review. You could also flashcard this and have like a pile of ones that need to be reviewed more and ones that you have more down so you don't need to review them as well or as much. So if you go through the table like that, that can be very, very helpful. But make sure you're not just memorizing names. Make sure you understand where the name comes from or why it's called that. So I'm going to briefly, very briefly, review that right now. So, and you should quiz yourself each time you see a name. Be like, why is that called that? Why is that arranged that way? Right? So for example, linear, well, it's a line, right? You can see the line that cuts through here. If we're talking about the shape of the molecule, it's gonna be a straight line. And it's gonna be like a bunch of these little like sticks floating around, essentially, if you were to look at the molecules bouncing around. Trigonal planar, it's in a plane. It's all on like a single plane, kind of like a piece of paper or like the surface of a table. And yeah, this is kind of like you're splitting it up into like 3 sections. I'm not sure why it's trigonal, but I think of like triangles and 3 or tri and 3. So I think that has to do with that. It might have to do with like the tri being 3. And then if we're talking about bent or angular, I mean that's kind of clear. It's not linear. You can see the shape of the molecule. It looks something like that. You don't, when we're naming the molecule shape, we don't include this in the shape. It's just like this kinked angle, which is really interesting because you actually get the same general shape here, but the angle is a little different because we've got more electron pairs down here. So this is also bent or angular, but the angle is a little different due to the fact that there's more orbitals pushing the electrons in those unpaired orbitals are pushing down on the bonds. So you can kind of see that this is still bent or angular, but different angles. The tetrahedron, tetra I think is 4, and then hedron's like talking about the 4 different surfaces that it has, because it's got like that triangle on the base and then 3 different sides. If you were to kind of like think of this as like a side, and then like that is like a side, and then that is like the bottom, and then this kind of like in the back, that back side. So there's like 4 sides to the tetrahedron, but it's kind of like these 3 there kind of going down, that one to the top. So then trigonal pyramidal, this has to do with the fact that there, if you were to look at the shape of this molecule, it kind of looks like a pyramid. Trigonal pyramidal is going to have like a base that looks like a triangle, and then you got like 3 points on the bottom, which are those outer atoms, and then the center one is kind of like the top of that pyramid in a regard. I kind of want to, just because it's so much easier to see this in the model, I'll just briefly go back to that. We were looking at, what was it? The trigonal pyramidal. So it's a lone pair and then 3 bonds. Okay. Yep, you can kind of see that top, and then the 3 here, and there's like the base, and then like 3 different sides, and then the base at the bottom, right? That's kind of what that looks like. Trigonal bipyramidal, you've got 2 pyramids, so that are triangles. So you've got like this triangle in the center, and then on the top, you've got this little pyramid, and on the bottom, you've got this little pyramid that goes to that, right? So it's trigonal bipyramidal, bi meaning 2. There's 2 pyramids that are trigonal, or are like, same sort of shape as the trigonal planar, especially with that plane that comes through the center there. The seahorse has to do with the fact that this, if you look at it with electron pair on the top, these look like legs for like a seesaw, and these would be those seats. T-shape, you can kind of see it's got 90 degrees, and then you've got these other 2 right here, so that's why it's a T-shape, is that the molecule is shaped like a T. This one's also linear. It looks very similar to this linear thing, but it's going to have like these 3 that are, if you were to look at the angle between these guys, it's like 120, right? Or the angle between this and that is 120. But we don't care about the angles between the electron pairs because they're not part of the molecular shape. So we can get rid of that. We're only really interested in the angle between atoms because that's really what you see when you look at these molecules. And then we've got octahedral. I think that's an 8-sided face. So you've got, yeah, like there's one face here, another face there, like this front, side, back. That's 4 sides, and then there's another set of 4 right here. It's kind of like, yep, let's go to like there, and that would go to like there. So you've got 4 faces on the bottom and 4 faces on the top. Square pyramidal, square base, and it's a pyramid, right? And then square planar, they're in a plane, like a piece of paper is in a plane, so it's like flat. And then this is T-shaped as well. It's actually, it looks like these guys are out to the side, getting as far away from each other, kind of like these 2 were. Yeah, so there's 3 instead of 2, but it's still T-shaped, And then this again is linear for the same reason that one was linear, with these guys all canceling each other out as much as possible, and the 2 atoms being on the opposite ends. Yeah, I know it's kind of weird to go through all of that, but it's better to have some context and be able to think about why the name is that way, because it's better than trying to just memorize all of these, because there's a lot of different combinations that you got to memorize. Try and clump them together. Think about how some are similar, like the linear ones are similar but a little bit different. The bound ones are similar but a little bit different. Yeah, it's I like to link a lot of things to tetrahedrons, and I like to link a lot of things to this general shape, and a lot of things to this general shape with the when you're separating 5 orbitals or 6 orbitals. So that's why they arrange them in tables, because it helps you to be able to compare them and think how they're similar and slightly different. If you're working with VSPER, you'll oftentimes be given a formula, and just from that chemical's formula, you need to figure out the bond angles and the geometries and the hybridization of that of that molecule. So for example, we've got this carbon and these chlorines together. You can think of the chemical being drawn out something like this. So you've got the four bonds, and they've got all these different orbitals filled out around the chlorines as well. So it's kind of weird. But if you were to look at the carbon, this is going to be a tetrahedron shape because there's four orbitals. That's gonna have it be like 109 degrees. So I'm just thinking about like my data table here. I'm like, okay, well, I know that I have four things, and carbon does not have any other lone pairs on it. So there's four bonds, and none of them are occupied by lone pairs. So four and none occupied by lone pairs. So you get that tetrahedron shape. And not only is that the electronic geometry, but that's the molecular shape geometry. So this is the name that you're usually going to be asked for, is like, what does the molecule look like? But we can talk about the general shape, which is like the same for each one of these rows. Like this, anything in this row is always going to, in general, be linear. Anything in this row is going to have an electronic geometry of trigonal planar, electronic geometry of tetrahedron for all three of these. These are all trigonal bipyramidal in terms of their electronic shape, not their molecular shape, but talking about electrons and orbitals. And these are all octahedral in terms of their electronic shape. Just some of them have filled in electron pairs instead of bonds. And so in that case, the molecular shape is going to be a little bit different than the electronic shape or that geometry. And so basically, if we're talking about the carbon, is four bonds. They have to be tetrahedron in terms of how they're separated. And with hybridization, it's basically the numbers that go above the S, the P, and the D. These are going to be reflecting the number of orbitals used or occupied. So like, for example, carbon has four orbitals that it's using. So it's sp3. And if you were to look at what it brought in, it was hybridizing 1s and 3p orbitals. So it kind of makes sense. Same with the chlorine. In general, the chlorine's going to have the shape of a tetrahedron because there's 1, 2, 3, 4 orbitals there, right? Like if we look at this one chlorine right here, there's 1, 2, 3, 4 orbitals there. And so one is being occupied by a bond, and then there's 3 that are occupied by lone pairs. So we can say this is tetrahedron. And it's actually going to be 3 lone pairs. Oh, this one wasn't even drawn on this table. So if this was an E and then an X, and then there's something like this, these are all lone pairs. This actually has to be linear. So this, when we're talking about linear, we can have also if there's just 2 things attached to each other, like A and A is attached to B, that's linear because it's 2 points in the line as opposed to 3 points in the line, right? Kind of can see that it's a straight line if you've got some chemical A, chemical B, and that's it. Then that's going to have a shape that's called linear, right? So this chlorine is kind of linear in how it's attached to the carbon, and it's going to have an sp3 hybridization as well. So that's the general idea with the electronic geometry and how that relates to molecular geometry. Kind of gets a little bit confusing for some people, but it's pretty consistent in how you see these used in these problems. So if we have BH3, we've got, let's go ahead and change the color for that. Should be something like this. I know from my periodic table that boron's going to be contributing, I think this is boron. It contributes 3, and each one of these is going to contribute 1 electron. So that should be what this chemical is arranged and what it looks like. You can also like count out, it's like 1, 2, 3, 4, 5, 6, and it should have 6 electrons in its valence shell. So if we're talking about angles on these guys, it's about 120, and not really applicable because there isn't really an angle between this orbital and the other ones because there is no other one. For the boron, this is what we would call trigonal planar. And that's actually the name of the molecular shape as well. So we've got trigonal planar. Let's go ahead and separate them kind of like this. And then we've got the hybridization of this would be, what is that, sp2? Because there's 3 orbitals, so there's 1 s and 2 p orbitals, I believe, being used there. Yeah. Yeah, it's kind of interesting because boron normally would have 2 electrons in s and then 1 in p, but it'll actually excite one of those electrons into another p. So you've got 1 electron in s, 1 in p, and another p, and then those can hybridize, right? And be attached to the electrons that the hydrogens are bringing in. So we also have, if we're talking about the hydrogens, this is linear for both, and just an s orbital for that one, because hydrogen does not have these other electrons around it. It's just by itself. So we're just hybridizing that s orbital. Okay. Then if we're talking about silicon sulfide, it looks like we're going to have some sulfurs here, something like that. I've got a feeling this is going to have some more electrons. Give me a second. I'm going to try and figure out how to arrange this. Okay, so I did skip that a little bit because it's not the emphasis of this video, but basically I counted out the number of electrons that you would normally get in the valence shell. Sulfur, silicon, it should have 16. 1, 2, 3, 4, 5, 6, 7, 8, right? There's 8 orbitals being used. That's 16 electrons. So this is what this should look like. You might want to put the electron pairs out on the sulfur here. And that would be like sp3 hybridized, and that's good. But then the silicon could be using more orbitals, so we might as well bring that in here and satisfy its octet rule and make sure it's using all of its orbitals in its valence shell. So you end up getting these double bonds in the center here. And we can say for our silicon and our sulfur that the angles on this for the silicon is going to be, I think it's 180. Yeah, this is a straight line. And then the sulfur, there's 1, 2, 3. There's 3 things that are in orbitals, these 2 pairs, and then the double bond. It's kind of weird. It does take up 1 orbital here, and then something else weird happens with the second one in a double bond. It kind of goes above and below, but again, college level stuff. But this occupies, you can essentially think that a double bond occupies a single slot for these geometries. So we're separating 1, 2, 3 things. So we've got like 120 for our degrees there. And then we can say for the shape here, this was linear and linear. There wasn't any unoccupied spots or lone pairs for the silicon. So the molecular shape is the same as the electronic shape. On the other hand, if we're looking at this, I think this is a linear because it's just A and B going from here. There's nothing else that's attached to the sulfur. So it's just got one thing it's attached to, so it's linear. But it looks to me like this would be trigonal planar. And then if we're talking about this in terms of the orbitals that are hybridized, gosh, I want to say that this is SP, and this is the SP2. I'm not sure. Is this SP3 or is this SP2 or is it SP? I wanna just double check that. Okay, so I did double check it. It is actually SP. The other p orbital that's above and below doesn't actually hybridize. So when we're talking about the hybridization, um, it's just S and P. So it's just like one, two bonds that are really hybridizing, and then there's something weird going on with those other ones. Um, yeah. So that's the silicon sulfide, and now okay, we've got C2H2. All right. When I see that, I'm just familiar enough with that to know what that looks like. Um, because the hydrogens are going to contribute one each. The carbons are going to, what is that, four each? So that's eight, 10. And yeah, looks like we got five bonds. So that has all of them in there. So if we talk about these carbons and the hydrogens, luckily both the carbons and the hydrogens have the same hybridization. There's not like carbon 1 or carbon 2 or anything like that that we have to mess around with. So if we're talking about the angles here, got 180 between them, and then this is not really applicable because it's only got one thing that's attached to, so there isn't really an angle between it and something else. Um, Linear and linear, I believe. And this is because there's the triple bond, kind of like the double bond, it only takes up one hybrid slot. And so carbon is going to have an sp hybridization, and then it'll have two p orbitals that are involved in this bond. It's kind of above and to the side of the hybridized orbital, and it's in that first bond. It's kind of weird, but I really like that stuff, and it's good to help you kind of understand it on a deeper level. So we've got sp hybridization. It's got one, two things that are being hybridized, and then looks like just S for hydrogen. Okay. All right. PF3. Now, I want to say that this is going to be oh, something like this, maybe. I know that phosphorus and sulfur are ones that they typically will have like some more bonds. Fluorine is going to be contributing 7. So times 3, and then P times 1. It looks like there should be 7 times 3, 21. And then this phosphorus, I believe, let me just double check on that. Where are you? Right here. It should have 5. Okay. So it should be contributing 5. And so it's a total of what, 26? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yep. 13 orbitals are being used, 26 electrons. Yeah, it's kind of a mess. So you can also think of 3, 6, 9, 12, 13. That's another way of double checking that you've got all of this in there. So yeah, that should be good. Phosphorus, fluorine. Let's have a look at what these look like. It's kind of similar to what we did on those last few ones. The phosphorus, it looks like there's 1, 2, 3, 4 things that are being hybridized. So this is gonna be like that 107-ish. And then the fluorine, it looks like 1, 2, 3, 4. Again, it's gonna be around that 107, 109, somewhere around there. Then if we're looking at the shape, this looks like is that a trigonal pyramidal? Is that what it is? I think that's what that is. So this is a tetrahedron for both of these in terms of the shape of the orbitals, including lone pairs. But if we exclude the lone pairs and we look at the molecular shape, I think this is trigonal pyramidal. I'm not sure about that one. I want to double check that one. But this one is definitely going to be linear because it's just a single point connecting, and the other ones are occupied by lone pairs. And if we look at the hybridization on these things, sp3, that's what you are seeing with tetrahedrons when you've got 4 orbitals. You have 1s and 3 p orbitals hybridizing to give you that. Let me just double check about that one shape. Tetrahedron, trigonal pyramid. Okay. I think you'd probably get credit for trigonal pyramidal, right? Okay, so that's how these problems kind of work. Thank you for joining me. This has been Andrew McLaren. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about, and remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia, and if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.